Okay, good morning to everyone. This is the seminar number 30 of this seminar series of the Magnetic Resonance Laboratory. And my name is Alberto, for the people who don't know me in the Zoom channel. And in this opportunity, we have a talk from France, Alberto Anadón, that is sharing his work with us. So now I will give pass to Carlos so that he can do the introduction. Carlos, go ahead.
Thank you, Luis. Just that I see that this screen, I suppose you mentioned, remember, the deadline have been extended for the workshop. So we have up to next Friday, in case you missed to send your abstract for either poster of oral contribution or just attend. Okay, so it's my pleasure, Luis, when you asked me to do the introduction to Alberto, I say, of course, yes. I mean, I'm very glad to introduce Alberto. Just let me say a few words about Alberto. So Alberto Anadón is from Zaragoza in Spain. I still don't know this beautiful city, but it's in the to-do list. And he did the undergraduate, master and PhD in Zaragoza in the group of Ricardo Ibarra, that's right, and with Miriam Aguirre, and then he moved to Madrid to do a postdoc in the group of I have a blank here in DEA, and the group of Paolo Perna, and he did a nice job. And lucky for us, he applied for a postdoc position in our group. And I say lucky for us because not only me, I mean, my colleagues, all the group were very happy to have Alberto in our team, and he's doing a great work, an excellent work, many things, participating in many projects. He's managing all that. I mean, particularly Sebastian, my colleagues, myself were very happy with that. Just to mention how happy we are with Alberto, that we would like to keep it in our group. But I mean, it is as a permanent reserve, but it's not up to us only. It's many factors we will see. So far, we still have Alberto for at least two more years. Hopefully, everything goes well. Well, just to add, Alberto is not for our colleagues in Magnetic Resonance Laboratory, because we have this ultimate project. For example, and several of you are coming to do secondment in Nancy, and one of the key persons that will come in you and help the people is Alberto. I mean, Luis, Jose Luis, and Ana, now Mara. So thanks Alberto for all this, and I hope you all enjoy his seminar. Alberto, you can start your talk.
Thank you, Carlos. Thank you very much for the introduction. I'm also very happy to be with you in the lab. I've learned so many things in the last few years from Joseph and all the people in the group. So today I will give some detailed review on the work that I've been doing in the last 5-6 years. And the title of my talk is High Quality Functional Materials for Spintronics and Spin caloritronic Applications. But I will talk about a very wide different things. First, I will give some small introduction about the motivation of my job, of the work I've been doing in these last years, and some basics on the physics that I will discuss. Then I will move and start talking about the work that I did during my PhD in magnetite thin films for spin caloritronic applications. Then I will talk also after about some hybrid epitaxial graphene monolayer epitaxial structures that I used during my postdoc in Madrid. And finally, I will discuss some recent results that we have here in ANSI in multifunctional ferromagnetic materials. So let me start with the introduction. And as most of you probably know, we have a big problem in society because we have too much data. We have the amount of data that we have in society is increasing exponentially. So 90% of all the data that we have stored today was created only in the last 2 years. So we need faster and more efficient ways to store and operate with this data. And as probably most of you know already, spintronics is one of the best approaches to try to overcome this challenge. And within spintronics, we have many possibilities. We can use, for example, spin orbit effects, and we will discuss this in detail during the talk, but we can also try to use thermal gradients, or we can use electric fields to change properties of our materials. And going into a bit more detail into this, we can also try to use the spin orbit interaction, for example, to create domains with chiral nature, and this can help also really well into going to more advanced and more efficient memories. Or we can take the spin orbit interaction also to do a spin charge conversion. And this can be done to achieve different things. We can also do memory with this. We can use it for energy harvesting applications. But for the amount of things that we can do with spintronics and spin orbit coupling in specifically is very high. And we can go even farther. We don't have to just look into spin orbit coupling in heavy metals or in these kind of materials, but we can also go to systems like topological insulators, RASBA systems, RASBA interfaces to achieve all of these goals. So furthermore, going more into the temperature interaction with magnetism, which is one of the most topics I will talk the most during this talk. So when we put together magnetism, electric currents, and heat currents, there is a very wide amount of phenomena that we are dealing with. And we can use this phenomena to achieve functionalities. For example, we can do modulation of the temperature locally using the spin Peltier effect or the anomalous Tinghausen effect. We can control actively the thermoelectric conversion using also these effects, but there's much more that we can do. So I will describe briefly some of the physics involved in this, in what's coming after, just for people that is not so familiar with the topic. So when we put together electric voltages and magnetic fields, we have the classic phenomena regarding resistivity. So we have the anisotropic magnetoresistance or the Planck-Hall effect if we are putting together a charged current with a magnetic material which is conducting, or if we look in the anomalous Hall effect and so on. But we can do exactly the same effects looking at temperature currents, heat currents, and magnetic field. So in here we were discussing electric currents and magnetic field, but we have similar behavior with temperature and magnetic fields. So these heat currents can obviously create temperature gradients, but when we put them together with magnetism, we also have some thermoresistive effects. And we can go further and we can involve the three different things. So we can put electric currents, thermal currents, and magnetic field. And we have all these different phenomena from the Seebeck or the Peltier effect. And if we go to the last, and all of this that we have discussed, that I have discussed in the last minute was regarding classical magnetoresistive effects, but we can go one step further and we can involve spin currents also in the system. And when we involve spin currents, we have also a new bunch of phenomena that we can discuss about, so like for example, the spin-Seebeck effect that can bring new functionalities also to our system, our devices. So just from all of this, I will now move to some of small examples of what we can do with this. So for memories, we have mostly now when we look at what's commercially available, the most used MRAM or magnetic RAM devices are the spin transfer torque MRAM. And these devices are widely known. We basically pass a current through the tunneling junction, magnetic tunneling junction, and we can write and read in this three-terminal system. But this system has some disadvantage, which is mostly that the current that we need to use to write is quite high, and one can damage the tunneling barrier. The process is also not fast enough for what we could desire, so it could be faster. And one way to try to overcome this is the use of spin-orbit torque. And spin-orbit torque comes from a spin-orbit interaction that I have discussed before. So what we can do is use spin accumulations generated by electrical currents in materials or systems with spin-orbit coupling to be able to switch the magnetization of a ferromagnet. And with this, we can create this kind of memories. There is mostly one big limitation. Well, there would be two, but one of the most important limitations is the fact that to have an efficient switching with a spin-orbit torque, you normally need an in-plane magnetic field to facilitate this switching. But there are already some advantages that we have been discussing in literature to overcome this and to have field-free switching. The other disadvantage would be that the electric current needed to switch and with a spin-orbit torque is also high, and it should be much smaller. So we need materials with higher spin-orbit coupling or better spin conversion in general to have the memories that we will desire. Another possible application of this spin-orbit interaction in some materials would be the harvesting of energy from waste heat. There is waste heat everywhere, and if we could take advantage of this waste heat to generate energy or to power some small devices, we will be in a much better position in the future to overcome all the issues that we are facing now. So one way to do this is traditionally we have been utilizing the Seebeck effect to do thermocouples like this to obtain power from heat, or if we go to the anomalous Nernst effect, when in a magnetic material, we can also do devices like this one, for example, to obtain energy from them. But we can do this from taking advantage of a spin-orbit interaction. If we do devices like this with a bilayer, with a ferromagnet, and a material with high spin-orbit coupling like platinum, we could take advantage of this spin-Seebeck effect to obtain energy. So I will move then to the first part of my talk. And now I will discuss magnetite thin film structures for spin caloritronics. So what I did during my PhD in Zaragoza, I prepared epitaxial magnetite thin films to study its spin current generation from incoherent thermal excitation. And I took advantage of this to generate charge current and power in a platinum layer attached to it. So basically, I was in charge of preparing these samples using pulse laser deposition combined with sputtering in the same chamber in situ. So we were able to prepare high quality thin films of magnetite using different substrate and different systems. As you can see, with very clean interfaces and low interdiffusion and high crystalline coherence, as you can see from the low oscillations in this X-ray diffraction theta to theta scan. So we were also able to characterize the surface of this system using a scanning tunnel microscopy. We were able to see atomic resolution in this system, which is quite complicated due to the insulating nature of the magnetite, especially at low temperatures. So we could see the different terraces of the magnetite and the antiphase boundaries defects in this system. So basically, from here, the message is we can prepare epitaxial magnetite thin fields with very high quality to then take advantage of them to do spin conversion experiments like we did in this system. So basically here, what we did was change the thickness of this magnetizing film from a few nanometer up to almost 300 nanometer. And we studied how was the spin current generation in the system. So to do this, what we did was measure the spin-Seebeck effect. We applied a thermal gradient in the out-of-plane direction using a resistive heater. And by putting two contacts to measure the thermal voltage and sweeping the magnetic field, one can see how this voltage increases as the power applied to the system increases. And by observing this voltage as a function of the thickness of magnetite, what we observed that there was a saturation with a characteristic length scale of about 40 nanometer in magnetite. And this is due to how the spin currents diffuse in the system. So basically we have a diffusion process which goes by this length. And this is related with how the magnons are moving or are diffusing in the system, basically. If we compare this to jig, for example, it's within the same order of magnitude. In some cases, it can be much smaller in others, depending on the quality of the jig. And so we move then to more difficult systems, to more complex systems, and we were able to prepare different multi-layers with several magnetic platinum repetitions. So we prepared also this using the same combination of pulse laser deposition with sputtering. As you can see, also the quality of the system is very high. When the number of repetition increases, it's possible to see that there's some relaxation of the material. So the system is not as crystalline as it's in the first layers, but still the layers hold quite good, as you can see in this TEM image. So what we observe in this system doing similar measurements is that the thermo-spin voltage increased by an order of magnitude almost when we have more than one repetition. So basically, by adding several magnetic platinum repetitions, this voltage increased by a significant amount, and then we observed also the same saturation effect. So we were able to explain this considering a more complex 3D diffusion model in which, as you can see, when you increase the number of magnetic platinum repetitions, the boundary conditions of the systems make the spin current. This is basically the spin current. The spin current in the system is much higher, and therefore the spin conversion in the platinum layers also increases, and then we obtain a higher thermal voltage in the end. So then our plan was to take advantage of these results and prepare some devices to obtain more a good power generation from them. So based on the system that I showed at the beginning of the introduction, we can do, based on the Seebeck effect, we can do Seebeck thermopiles, or if we are using the Nernst effect, we could do these Nernst thermopiles. And for the spin-Seebeck effect, we can use similar design as the Nernst thermopile. So this is what we did. We did two different designs. First, we used one device in which we had in series a magnetite platinum system and a gold contact in here. So in this case, we can sum the voltage of all these different magnetite platinum terminals, let's say. So our goal here was to have a much higher voltage output in the end. And the other approach that we took was to use one of these devices in which we contacted this in series with different smaller terminals to have a higher, like our guess was to have a higher output due to the parallel nature of all the current, spin current generated in the system. So this is the voltage measurement. In the first design, we observed that the voltage is increased by kind of an order of magnitude. This is what we expected due to this different design of the device. But when you connect a load resistance into the system to obtain the power, we were surprised to see that the power that we obtained was highest in the case of the complete bilayer. So we are comparing here both devices with a single bilayer with no lithography in it. So basically the power that we obtain in the system, we see that it's related with the area of the spin conversion. So the larger the area for spin conversion that we have, the more power we are able to obtain from our system. Okay, so with this, I will move to our next part, and I will talk now about some hybrid epitaxial graphene monolayer with metal structures for spin orbitronics. So we are all familiar with graphene and other 2D materials. Graphene is a very interesting material for spintronics because it has a very long spin diffusion length, and it's possible to tune graphene with different materials to change its properties, and we have seen this for several years already. So what we did, we were able to prepare in Madrid, in India, we were able to prepare these complex structures completely in situ without breaking the vacuum. So we have a fully epitaxial stack and also using offsite substrate. So this is very interesting because it allows to do devices. Normally, to grow graphene by CVD requires to have some metal substrate, but we can overcome this problem by using some small thin film of several nanometer, like from 10 to 100 nanometer thick, in which we can grow epitaxially on oxide substrate. Then this is done typically by sputtering at high temperature. We can use this buffer system to then grow a monolayer of graphene by MBE, as I said, without breaking the vacuum. So we have a clean system. Okay, then now we move this, as you can see, we still have a clean surface by observing the lead images. These arcs here are related with how graphene grows on top of our material. Basically, we have some rotational domains that are due to some defects in the graphene. And then we can take this sample and we grow using molecular epitaxy. We can grow a thin film of cobalt on top of it. Now we lose all our currents in the surface because everything that you try to grow on graphene, or most things that you try to grow on graphene, tend to grow in island because graphene is very surfactant. So things tend to accumulate. And then what we do is we heat this sample, and then the cobalt tends to travel in the surface of graphene and goes beneath graphene. So we have now, when cobalt does this, it becomes an epitaxial layer just below graphene. So what we have in the end is a sample on an oxide substrate in which we have a completely epitaxial stack for that we will use then later. I will show you now the characterization for this. So in the end, what we find by TEM image is that we have a FCC cobalt, which is pseudomorphic with platinum, with very few dislocation or faults, and very small intermixing and so on. So basically, we have, as I said, very high quality samples prepared using this method. One of the most interesting things of this type of stacks is that the perpendicular magnetic anisotropy of cobalt increases significantly up to 4 nanometers. So normally, the reorientation transition for a platinum cobalt platinum system goes between 5 and 10 monolayers of cobalt. But if you have a graphene cobalt platinum system, this perpendicular magnetic anisotropy is held up to almost 4 nanometers. So you can have much thicker cobalt with still having perpendicular magnetic anisotropy. So in this system, we were very interested in understanding what was going on in the graphene-related interfaces. So basically in our cobalt graphene interface. So we studied how the intercalation process of cobalt went. And what we found by looking at the 1s peak of carbon in X-ray photoemission spectroscopy was that when we have a platinum graphene sample, our C1s peak was shifted to the right. So we have p-doped graphene when it's grown on platinum, only on platinum. But okay, now we put the cobalt by MBE on top of it, as I described in the previous slide. And there is a new peak showing up here. So we have a combination of two different peaks in the C1s of carbon. Then when we heat, the cobalt goes below the graphene, and all the first peak that we have is completely shifted to the left. So we have a very efficient intercalation of about almost 100% of the cobalt in the system. And now, as you can see, the peak of carbon is shifted to the left. So now graphene is n-doped. So we are creating an effective electric field perpendicular to the interface. And this is very important because it's what happens in Raspberry interfaces. So we thought that this could be one thing we could take advantage of to create, for example, chiral domain walls. So the origin of chiral domain walls sometimes comes from the EMI interaction, the Alberto interaction. And it's possible to measure this effect, these chiral domain walls, studying how pulses, with pulses, how domains grow. So if we take, for example, domains like a domain like a circle, we can apply pulses of magnetic field, and going up or down, we see that in a platinum cobalt platinum system in which the DMI is 0, we see that when we go from up to down or down to up in the magnetic field, we have a symmetric system. But if we look at the graphene cobalt platinum system, we don't see the same effect. We have a different behavior going up and down or down and up. And this is related with the Deleuze-Schemori interaction. So basically, we are able to compute how much is the Deleuze-Schemori interaction in the graphene cobalt interface, and is within the same order of magnitude that one that we can see in the cobalt platinum interface. And this is very interesting because in principle, graphene is very weak in terms of spin orbit coupling. So what's happening here should come from the graphene cobalt interaction or the graphene cobalt interface, and not from graphene itself. So what we did with these samples was to study this interface. We took these samples to the synchrotron, and we were able to measure in more detail the photoemission spectroscopy with angle resolve and spin resolve bands. So basically, we measured the bands. This image show the bands of an iridium graphene system. And you can see here the pi bands and the sigma bands of graphene. This is 62 electron volts of photon energy. And then when you intercalate, you grow the cobalt and you intercalate, you see this same shift in the bands that I showed just a few slides ago with XPS. And this is related to this electric field that I was just discussing about. We can also go and see how is the spin splitting in the bands. And basically we find that we have a significant spin splitting. This is in the same order of magnitude that some first principle calculations that we have done in a graphene cobalt with 3 monolayers system. So if you are interested in this, you can have a look at our recent papers, and you will see this is still unpublished, but all the calculations are already published. You can look for them. Okay, so we can now let's take advantage of all the physics that we have obtained from our graphene samples. So as you know, I discussed this before. We can use the inverse spin Hall effect, for example, in platinum to generate spin currents, spin currents or charge currents, or convert one to the other. So we can do this also in interfaces, as I just said. So let's take advantage of the graphene cobalt interface to do a spin conversion. The system that we took first was an iridium cobalt heavy metal, and in here we will put platinum and tantalum. And so we will compare iridium cobalt platinum with iridium cobalt graphene platinum. Here we are introducing a graphene interlayer, and we studied what is graphene bringing in terms of spin conversion to the system. Same as before, we have very nice samples with clean interfaces, small interdiffusion, and high quality. So now let's move to the measurements in Thermo-spin. Here I'm showing the comparison between an iridium cobalt iridium. So in this system, basically we are seeing mostly the anomalous Nernst effect, and in here we are comparing the other two samples that I just said: iridium cobalt platinum and iridium cobalt graphene platinum. So at first, just by looking at the voltage that we obtain when we sweep the magnetic field with a thermal gradient in our sample, we already observed that graphene is reducing significantly the voltage that we have. And so then this is a first measurement. So we need to compute how big is the anomalous Nernst effect in the system to subtract it and to really estimate what's the effect of graphene in the system. So we did this, and we compared also with tantalum samples, and we are observing a similar behavior both in platinum and in tantalum. After removing the contribution from the anomalous Nernst effect, we see that that graphene is reducing the total spin conversion in the system. So this we think that this is due to a combination of several different things. One is the possibility of introducing a spin memory loss in the system, but also we have graphene can be highly affected by what has next to it. So platinum and tantalum can affect how graphene behaves in terms of spin conversion. So we have a combination of different things that are making that are pointing both to the same direction, to the reduction of the thermospin voltage in the system. But we can go further, and we can study not only what happens in 2D materials, but also in interfaces. And there are different phenomena that we can see in interfaces between different materials. So I discussed a moment ago about spin memory loss. In here, when we introduce a spin current in the system, in the interface with a spin orbit coupling, we can, for example, lose part of this spin memory of this spin polarization, and this, as I said, this is called spin memory loss. But we can also have different effects. Basically, we can have, for example, spin filtering, in which a current that can be even unpolarized in terms of spin, we can create a spin polarized current in both sides of this interface due to this Raspberry interface in the system when we have a electric current in our stack. But we can also have other effects like spin precession, for example, also able to change the spin polarization of our spin current. And to study these effects, we prepared stacks like this: platinum, cobalt, platinum, with a copper interlayer between 0 and 3 nanometer. And in here, our plan was to study what's the effect of the interfaces in copper in this system. So as we introduce this copper interlayer, we can already see that the perpendicular magnetic anisotropy of our system is reduced. So from the platinum cobalt platinum with no copper, we are seeing that the loop is tilting, and this is due to the reduction of the perpendicular magnetic anisotropy. And the experiment is to study how this copper interface affects our spin orbit torque. So in principle, if our copper is completely transparent and the interfaces of copper play no role in the spin orbit torque, we should see a constant, almost zero spin orbit torque, since the torque coming from the platinum on the bottom and top should normally compensate, since the thickness is similar. And copper is almost transparent in terms of spin current. Spin diffusion length is very high. So with any effect that we observe here should be related to the interfaces with copper. And what we observe here is that when we introduce this copper interlayer, the spin orbit torque is increased significantly, both the damping-like and the field-like torque. So for no copper, we see almost no torque. And when we put some copper in it, the torque is much higher. And what we are seeing here is basically we are breaking the symmetry somehow, and we are introducing a spin orbit torque because the effective SOT coming from one layer is different from the other. So to understand what's going on in the system, we studied the spin Hall magnetoresistance. And the spin Hall magnetoresistance is a double spin conversion process. So we have at first a spin Hall effect in the platinum layer, and also inverse spin Hall effect coming back to this. And the combination of these both effects is giving some changes in the longitudinal resistance of our sample. So basically, if we apply a current in this direction and we measure in the longitudinal direction, we observe this kind of behavior when we rotate the sample in this plane. Okay, so we studied how this magnetoresistance evolved in our system, and we see a significant decrease of the spin Hall magnetoresistance when we introduce the copper interlayer, and we ascribe this fall of the spin Hall magnetoresistance to an increase of the spin memory loss due to the introduction of copper. So basically, the spin memory loss is reducing the spin current in the system significantly, but this cannot explain everything that we are seeing. So basically, if we go further to even up to 15 nanometers of copper, and we put everything in a diffusion model to understand how is the spin accumulation and spin current in the system. If we have no spin memory loss, we would follow something like this. So basically, copper will be almost transparent, and we will see no changes in the spin Hall magnetoresistance. If we add the spin memory loss, we will be somewhere here, but we cannot explain what's going on in the middle of this thickness evolution only using spin memory loss. So we believe that there is a spin current generation in the interfaces due to these processes that I described at the beginning, due to spin filtering and split profession. So now I will move to the last results that we are developing now in Nancy, and I will talk about gallium iron oxide (GFO). This material, we believe that it's truly very interesting for spintronics, since it's first a ferromagnetic insulator. We don't have too many magnetic insulators that we can use for spintronics, so it's very interesting to have another one. But also it presents magnetoelectric properties, so it's possible to change its magnetic properties using an electric field. So what we are doing this in collaboration with our colleagues in Strasbourg. They are able to produce these samples by pulse laser deposition. As you can see, also, I'm very lucky with all my collaborators because they are also able to grow very good samples. And as before, they are very good in terms of crystalline coherence and clean interfaces and crystalline systems. So the first thing that we did when we got these samples was to study also the spin Hall magnetoresistance in the system, because this can give you an idea of how good is the material in terms of spin current generation. So we observed that the spin Hall magnetoresistance is comparable to the one in GIG when we put this GFO system in contact with a platinum top layer. And we observed also that the proximity effect in the anisotropic magnetoresistance due to proximity effects in platinum could lead to anisotropic magnetoresistance, and we observed that these are not very important, especially at higher temperatures. So spin Hall magnetoresistance basically dominates all the magnetoresistance in the system. And furthermore, we can take advantage of this material also to thermal devices. And what we did was devices like the one I'm showing here. Basically, we have our GIG thin film or GFO later on. We can grow a platinum layer on top of it. And then to measure its thermo-spin properties, we place a silicon oxide insulator layer on top of it, and then we grow a gold heater. So in this case, we can locally heat our sample, which is very interesting because it will allow us to have more reproducible measurements than in the case of full thin films. And this is how the devices look when we may look at them at the microscope. Basically, here we have our heater, here we have our sample. This small square here is the silicon oxide in between both terminals. And if we apply a current in this heater, we are heating in the out of plane direction, and we will observe this kind of course when we change the power. So each of these loop is a different power, which then the saturation voltage, as expected, increases linearly with the power that we are introducing in the system. So this is a good indication. And we can go and measure also this in GFO. So GIG, as you know, GIG is the yttrium iron garnet, is the cornerstone of spintronic ferromagnetic materials in terms of insulating materials, because it's one of the most used generally. So we can see just by comparison that we have a similar voltages in both yttrium iron garnet and GFO devices, that similar to the ones that I'm just showing. In addition, if you look carefully, you could see that the hysteresis loop is shifted when we are increasing the heater power, and this also scales mostly linearly with the heater power. We believe that this is related with the magnetoelectric nature of the system, so we could have some pyroelectricity making this offset change, but we are not 100% sure about this. So now, to be able to really compare carefully both systems, the first thing that we did was develop a one-dimension heat flux simple system, so simple model. So basically, just using Fourier law and knowing the thermal conductivity in our system, we can make a rough estimation on how much our heater, our thermal gradient in the ferromagnets is if we assume this one-dimension heat flow and we know how much power we are introducing in the system. But we can go a bit further. We can do also finite element simulations. And if we look at the device, basically what we observe is that this is the heat flux profile. So the heat flux is producing the gold heater. This is why it's increasing here. Then it's mostly constant through the whole device in the GFO, for example. And then when we reach the substrate, since the substrate is much bigger, then the heat flux goes through all the substrate and is very soon almost zero, as you can see in the inset here. So we can look at the temperature profile, and we can calculate from this using this simulation how much is the temperature gradient in our magnetic system. And basically, what we observe is that our first guess estimation was mostly correct. So we can compare using this both this simulation in addition to the one in yttrium iron garnet. We can compare the spin current generation from thermal origin in both systems. And to do this, we introduce this spin-Seebeck coefficient, which is basically the voltage coming from the inverse spin Hall effect normalized by the heat flux and the resistance of our detecting layer. And if we compare this in both systems, we see that the spin current generation is mostly similar in both systems. So basically, we are introducing to the community this new ferromagnetic insulator material with magnetoelectric properties, which is able to generate spin current mostly as good as yttrium iron garnet. So with this, I conclude. First, I talked about my motivation to develop my work and some of the physics involved in it. Then I discussed a bit how the spin current is generated and converted in magnetite platinum multilayers. Then I introduced this new graphene monolayer system in epitaxial stacks with other metallic materials, and how the graphene interface can be very important in spin conversion experiments and in spin orbitronics in general, and how can we tune graphene to obtain the properties that we need. And finally, I introduced this multifunctional ferromagnetic insulator material to the spintronics community in terms of thin films. So just to finish, I would like to acknowledge all my collaborators, Miriam and Ricardo in Zaragoza during my PhD. Also all the people in IMDEA, Paolo, Julio, Ruben, and everyone there. And finally now Seb and Carlos, which are helping me and teaching me a lot here in Nancy. So thank you very much, and thank you all for coming and seeing the seminar. If you have any questions, you want to comment anything or just discuss, please go on.
Good. Thank you, Alberto. This was a really nice presentation. Yeah. One is clapping in the conference room. So yeah, they like also the talk. So I would like to open now the session to questions. We already have a question of Laura. Laura, you can go ahead.
Hi. Hi. So I had a question about graphene.
Mm-hmm.
How did you grow graphene in UHV? And if you checked afterwards by Raman, your graphene layer?
Okay. So let me go back to the slide where I discuss this. Here. Okay. So what's normally done by this is chemical vapor deposition. Okay. So normally what people do is you have a copper monocrystal, for example, or iridium or platinum monocrystal. You heat this crystal to very high temperature, normally about 1000 or 800 Kelvin, and you put a bit of gas in your chamber. This gas, when it reaches the surface of your metal, it breaks the bonds between this, usually ethylene, but you can use a different one. Then the carbon hydrogen bonds are broken, and then carbon sticks on the surface. And since this monocrystal is usually hexagonal on top, hexagonal structure, so basically the carbon mimics the surface that it finds. So basically you have then this graphene monolayer. So the novelty in these samples is not this, because this has been done for a long time already, at least several years. The novelty is that we are using oxide substrate. So we can do a few nanometer of platinum or iridium growing by sputtering, and then we heat the sample in the same way, and we put gas in the same way. So the growth process is basically the same as we'll use in a monocrystal, but you use a thin film. And then this thin film can be then patterned, or you can do as you want, and to for example, prepare devices to measure anything that you want. Normally in a monocrystal, you are not able to do this because since the monocrystal is almost zero resistance, you cannot apply any current through the graphene itself. But in this case, even though you still have some metallic material, which is much more conducting than graphene, the proportion is much better for devices. I don't know if I answered your question.
Yes. Also, you say you are doing
about the Raman. Sorry, the Raman. I'm not sure about this. Maybe Paolo can comment about this. I think maybe we did it, but I'm not sure.
Okay. Also, you say you put it on top of an oxide substrate, but you cover that oxide substrate with the metal to catalyze the process of graphene. Okay. And then how thick is your cobalt for it to go through the graphene?
So we have done, I think, up to 5 nanometers or so. If you have a very thick cobalt layer, then it's hard to do the full intercalation. So the thicker you want, the harder it is. But as you see here, we've done 4 or 5 nanometer, and the intercalation was almost 100%. But yeah, as you grow thicker, it's much harder to grow to the sample.
Okay. Well, thank you very much. It was a very nice talk. Sorry.
One way, just to finish, one way that. So if you can, graphene protects your cobalt, because normally if you grow a 5 nanometer cobalt layer and then you take it out of the ultra high vacuum, then it's completely oxidized and you lose all the magnetic properties of your material. But for example, you can, one of these platinum cobalt graphene, like here, you can take this sample out of vacuum without any problem. And this is basically how this was done. You go to the Kerr microscope, to the magnet-optical Kerr, and you measure the hysteresis loop, and you keep the hysteresis loop out of vacuum because graphene protects your cobalt layer. This is another of the applications of your graphene. Okay, so you could do Raman afterwards, just to check you have a. I'm not an expert in it, but it's, I guess it's possible. Maybe Paolo, if you want to comment.
Yeah, if I can. Hello to everybody.
Hello.
Hello. Just to comment about that. The graphene here is a monolayer graphene epitaxial on top of this idly interacting metallic buffers. So in this case, the signal from Raman is completely or almost completely suppressed by the substrate, the heavy metal. We tried several times to do this Raman measurement, but we never got the peak. Different is the case of freestanding graphene that you transfer, for example, on top of copper, whatever substrate. In that case, you have the signal from Raman and everything is okay. But anyway, the lead pattern already is indicating you that you have graphene. For example, this in the third image here, you can see the typical feature of the graphene on platinum. Due to low interaction between the graphene and platinum, you have these rotational domains. Then when you grow on top cobalt, you lose the graphene, the lead, and then when you intercalate, you get exactly the same picture that you had before. And in case of iridium and ruthenium, you can even see the Moiré pattern. Okay, so this is already a proof. Doesn't. Perfect. You don't need to do also Raman, but it's good. Thanks. You're welcome, of course. Okay.
Thank you, Alberto. Also.
Thanks, Paolo. Thanks, Laura. Javier Curiel, a question.
Okay. Hello. Can you hear me?
Yes.
Mm-hmm. Yes, thank you. Very nice talk. I have a question regarding this sample. In slide number 20, I guess, you show that the threshold for the PMA shift, on that graph. Are you sure that the change is due to the graphene or due to the crystallinity of the cobalt layer?
Even if you
can you say something about that?
Even if you grow epitaxial cobalt in these kind of systems, I don't think you will get much higher than this reunification transition. Yeah.
Okay. Did you characterize the domain wall dynamics in this kind of samples? I just particularly I want to know how the deepening field change, because that will change with disorder, and I want to know if to put the graphene increase the disorder or decrease.
I cannot tell you because I did not do this measurement. You probably can ask Fernando if you want, but I'm not sure. I'm not sure.
Okay. Well, thank you very much.
Okay, I have a question also. In the measurements of SOT in platinum, cobalt, copper, and platinum, you show that you have a transition from out of plane to in plane magnetization, but that is not reflected on your results. In the next slide, you cannot see, or you are not able to see any influence of the in plane to out of plane. Yeah, in that one.
Okay, so this is not in plane an in plane system. You can see it's also not completely out of plane and square. But if you look at the in plane hysteresis loop, it's like we call this weak PMA because it's not real full PMA square loop, but it's also not in plane. What we do to measure spin orbit torque here is we apply because we are able to apply field in two different directions. So we apply a small field and we go in here in the saturation state, and then we measure the first and second harmonic in here. That's how I do these measurements.
Okay.
You know what I mean?
Yeah.
Because if you look at the anomalous Hall effect in here, you will not see the normal features of the first and second harmonic. So you have to go to saturation basically. But you can still measure a spin orbit torque even if you don't have a full square hysteresis loop.
Okay. Okay, I understand. Thanks.
I don't know if that is exactly your question, but
yeah, more that because we see a tilt or sorry, a loss of PMA in the in this curve, but
yeah.
No,
This is basically because the origin of the PMA in this system is basically the interfacial anisotropy from platinum cobalt. So when you lose this this interface, so for thinner copper, there can still be some interaction between the platinum and the cobalt. This is what you see here in the 0.5 nanometer. But when you have thicker than this, then the effect of the platinum on top it's already lost very soon. So yeah, basically, since you don't have the perpendicular, since you don't have the interaction between the cobalt and the platinum, you lose this interface, this interfacial anisotropy, and then your cobalt goes a bit more in plane. But as I said, this is not fully in plane.
Okay.
It's
okay.
kind of tilted out of plane.
Okay. Yeah. Thanks. I think we have a question in the conference room. I think Elin is.
Yes. Hello. Good morning. Very nice talk, Alberto. I have a question about the first system that you present, the magnetite over the magnesium oxide, because the magnetite tend to oxidize and tend to magnemite, so the properties of half metallic, it goes, well, it's degrade the material. So have you measured how your spin-Seebeck effect change if the surface is oxidized, and if you evaluate, well, this effect in your samples?
Specifically, these ones are like are perfect magnetite. You can tune this by the growth properties, as you probably know. We have done some studies in Magnemite, and I think that the spin-Seebeck is in the same order of magnitude. The difference is Magnemite is completely insulating, while magnetite is a bad conductor, let's say. So in this case, you also have the Nernst effect. Probably this will increase the total signal that you have. But I'd say that I cannot remember exactly, but if you want, I can send you some references. And I think that our conclusion was that the Magnemite, the spin current generation was more or less similar to that magnetite.
Thank you.
Thank you, Lynn. And I have a last question. In the GFO system, how did you fabricate the sample with the PLD?
Yeah, this is this was done in Strasbourg. I didn't do it, but it was done completely by PLD. So they grow both the GFO and the platinum by pulse laser deposition without breaking vacuum. So yeah.
Okay, thank you. Is there any other question in the chat or in the conference room? If not, I would like to thank you, Alberto, again for your very nice presentation.
Thank you, Luis, for the invitation too.
Yeah, no problem. You're welcome to present your result whenever you want. So, and for the people who arrived late, I will have to remind you that the deadline for the abstract submission of the SPIN Argentina has extended up until 17. So you have a few more days to send your abstract if you have not done. And thank you everyone for being here, and see you again next week. Goodbye. Thanks.